Good afternoon. We are Innovative Structural Designs. Our project was on the Grant Street Timber Bridge located in Titusville, New Jersey. It spans the Delaware and Raritan Canal, which connects the Delaware River to the Raritan River. It was previously used to transport freight between New York and Pennsylvania. Our team members include myself, Ian Edison, civil engineer, CAD operator, and I'm in charge of load modeling. Sean Nagy is the civil engineer, material researcher. Darren Rawling is actually a mechanical engineer. He'll be the vibrations analyst and team leader. Kevin Walsh is also a civil engineer, and he's in charge of the codes. He's the codes expert. So our motivation behind the project, the American Society of Civil Engineers puts out an annual report card to show how deficient the America's infrastructure is each year, per state and then also for the United States of America. You'll see here 36% of bridges in 2006 are structurally deficient, meaning they need repair. 2013, you'll see that America's bridges got a grade C+. You can see here the percentages, which are actually beginning to decrease and the grades are starting to go up. We're hoping that our final design can help, aid in bringing these percentages down for timber bridges. So our goal is to prove that wood can be used as a timber bridge structure, can be used for the bridge superstructure instead of using steel and concrete, which is more widely used in the world today. We also, in turn, want to build our skills necessary for our engineering futures. We recently came in contact with the FHWA, which performed an inspection on the existing bridge here, which was built in 1950. It was renovated in 1988. The inspection was done in 2010, and the status for the inspection was that it's structurally deficient, meaning it does need repair. So we are designing a remodeling of the bridge, a new bridge frame and bridge deck. We're going to use the existing abutments. Here's our project block diagram. You'll see here that the project is divided up between the technical and non-technical constraints, and once we found the materials, the treatments, and the loading by AASHTO to use, we can start coming up with a preliminary design, which we have almost completed a preliminary design. And once we do complete it, we are going to test it and make changes accordingly and continue to improve our design until we come up with a final design for it. So the technical design constraints, you'll see loading. It needs to follow AASHTO LRFD bridge design specifications. So that's going to be most of the calculations we'll be doing. The dimensions overall for the bridge, the length is 30 feet. The width of the road is going to be 28 feet, and we're going to have 5-foot sidewalks on either side, which will total to be a 38-foot width. It's actually wider than it is long. Material that we chose to use is southern yellow pine. I'll explain to you in the next few slides why we chose that material. Code requirements, we'll be using AITC, AWPA, and the ADA codes, as well as AASHTO and the New Jersey Department of Transportation specifications. Our testing will be done, since it's such a large bridge, we can't physically test it, so we're going to be doing all of our testing in StatPro and SolidWorks, and then we'll use hand calculations to verify StatPro's analysis. Non-technical constraints, assembly, ease of construction. We've decided to prefabricate most of the parts for the bridge off-site and then have them assembled nearby, and then hopefully have it crane lifted onto the existing abutment after the old bridge has been removed. We feel like that's going to lessen the impact to traffic in the local area, and will also allow for less debris, around the area for the river, keeping everything clean. Environmental concerns, we want to make sure that the bridge is environmentally safe for both wildlife and human life as well. So we need to watch our treatments and preservatives for that. Sustainability, we want it to last long but also have minimal maintenance. So that's very important. And manufacturability, they need all the materials that we're using need to be strong enough to meet the necessary standards, and it includes like the wood treatments and the hardware. Health and safety, we'll be abiding by ADA regulations for the ramps, for the sidewalk, and using handrails to help with the safety there. We also have to do curb design so that the pedestrian walkway is elevated away from the road so that pedestrians are safe from vehicular traffic. So in terms of the wood materials, we came down to the two main ones, Douglas fir and southern yellow pine. These are two of the most widely used American softwoods. This is listing all the American softwoods that are used in construction in America. So here you can see that the Douglas fir and the southern yellow pine have the highest values across the board for specific gravity, compressive strength, bending strength, stiffness, hardness, everything that matters in timber construction. So the type of southern pine that we decided to go with for our glulam beams, which most of our bridges consisted of glulam material, which is basically just wood that is laminated with an adhesive in layers so that you're getting the most strength out of your timber members. Glulam members are the strongest members among timber construction. So we chose 24F-V3 because the bending strength is 2400 PSI, and the V3 stands for the 300 PSI of shear strength. So this is one of the strongest types of glulam. Now this can be modified later on if we don't need quite that much to drive down the cost a little bit. So that can be adjusted later on for our members. So in terms of the deck design, we were debating between plank decking or glulam decking. The plank decking is cheaper, but it also is not as strong as the glulam decking, and it doesn't protect the superstructure underneath as much. So we decided to go with the glulam decking. A little more expensive, but it's much stronger. It protects the superstructure better than the plank decking. So that's our decision there. In terms of the drainage design, we're also going to be doing that over the summer and next semester by cambering the stringers and putting a slope on the sidewalk so that water can flow off. Final design for treatment here. We're going to be using ACQ, which is it's waterborne. This is going to be for the railings and the sidewalks. It stands for alkaline copper quat, which is a better option than the chromated copper arsenate and the ammonial copper zinc arsenate, which they're both highly toxic to wildlife and humans. So we decided to go with the ACQ because it's newer and it is just as good as these. So that's been very commonly used. For the decking and the stringers, we're using pentachlorophenol, which is oil-borne, and this is going to be the most widely used preservative for timber construction. So we decided to go with this because the alternative was highly toxic, highly flammable, creosote. We decided not to use. So they're both water repellent, which because this is sitting about 2 feet above the water, that's going to help. With rain and everything, it'll lessen the decay and increase sustainability. The railing and the sidewalk design. So you'll see here, these are the constraints we have for the railing and the sidewalk, which we've done the railing and the sidewalk design already. I'm going to go to the next slide because it explains this a little bit more. Using the AASHTO method for this, your W is the weight of the vehicle. The B is the distance from the bridge deck, the road surface, to the center of gravity of the. B is the width between the tires of the vehicle. G is the distance from the ground to the center of gravity of the vehicle. The crash angle is 25 degrees. In TL1, we decided to use this instead of the others because this is designed for local streets, low volume and low speed. So using these factors, we can design the crash rail so that it's safe, so that cars don't go off the side. The final design for connections. This is showing the connections from the glulam decking to the glulam stringers. Here you can see they're kind of L-shaped here, but it also has a hook to help increase the strength. All the steel bolts, nuts, washers, they need to be hot dip galvanized. That's required by AASHTO and ASTM. They're showing here the bolts are 5/8 of an inch in diameter, 11 threads per inch, 8 inches in length total. Also attaching the abutments to the bottom of the glulam girders. We're going to have pins on one side, a roller on the other, to allow for expansion and contraction and different temperature changes. The diaphragms, this is what you see here. This is one of our preliminary designs, but we kept it as we got to our newest one. So you can see there's 12-foot spacing in the center, 3-foot spacing on the outside, and you'll see that along those lines it's 6 inches oscillating back and forth. This is showing a view from the side of how it's going to be connected to the glulam stringers. So that's our diaphragms. These are the overall dimensions of all of our members for what we have so far. You'll see that the difference for the two main stringers is about 6.75 inches, which allows for a curb height and to lift our sidewalks above the road surface. Here's a front view of our bridge. This is showing the existing abutments. There are 3 abutments right now. We're not going to utilize the middle one, but all 3 abutments are the same. You've got 5 columns that are 12-inch diameter and then a 12-inch square beam that goes across. So that's showing the front. Here's the side. You can see that we don't need the middle abutment because we're using glulam stringers. With the dimensions that are given, they're strong enough to withstand that span. That's one of the big benefits to using the glulam. Here's an isometric view from below. You can see the diaphragms here. You can see the outside bracing, the inside bracing, and then everything else. It's going to be crane lifted in, so we're kind of showing how that works. This is once it's attached to the abutment. What we have so far, you can see the 5-foot sidewalks, 28-foot road surface. Our railings are there, and what we got to keep in mind is that the road surface is going to be slightly below, so we want to grade that so that there's a smooth transition between the existing road and attaching to the bridge itself. Load testing, this is very important. So this is where a lot of our calculations are going to come into play with testing. So we have the dead load, which is going to be the overall weight of the structure, which most of it is going to be, I think all of it actually, is southern yellow pine, which is a density of 37 pounds per cubic foot. We can use that to get the overall weight, and that'll give us our dead load. And then live load is going to be a combination of the worst case scenario. We're designing for worst case scenarios. So you have 2 tractor trailers going opposite directions. We're going to have 6 concentrated loads for each tractor trailer. You can see the 32 kips, 14-foot space, and the 8 kips for the front. So we'll have a total of 12 concentrated loads across our bridge because it's only 1 lane each way. And then also we're going to have a design lane load of 640 pounds per linear foot over the 10-foot width throughout the length of the bridge. So designing all of that and factoring it all will give us what our overall loads are going to be, and we can calculate to make sure that there's not too much deflection, and this will be possible. Vibration testing, this is going to be Darren's job using SolidWorks. Basically this is showing your the mode. Vibrations, this picture is showing the mode shape. So SolidWorks will produce a similar one for us for our new bridge, and what values that we get from our SolidWorks testing from the vibrations here, 10 years down the line, they can hook up accelerometers in the field and actually do the same testing again and compare the differences in the values to kind of determine if there are points that are starting to break down or weak points in the bridge. So that can help in the future. This is showing finite element analysis, which is what SolidWorks' calculations are doing. It's breaking our bridge down into small pieces, calculating every vibration from a finite element, and this is showing the numbers of elements that we have here. Degrees of freedom are showing the X, Y, and Z direction that it can vibrate, and then the moments in all 3 of those directions that it can vibrate. Okay, so that's that. Here's our cost estimate. We've called a few different glulam companies, hardware companies. We're getting all of our cost estimates together. This is our preliminary total material cost, $63,426. That's excluding labor, so trying to keep it under $120,000, including labor in the end. Schedule. And major design and challenges and risks. We want to make sure that the materials that are being used are appropriate, as you can see here. Design. We need to make sure that everything follows the New Jersey Department of Transportation specifications, which often refer back to AASHTO. So we've been using AASHTO and the ITC manual for most of our work. And the ease of construction, like I was telling you earlier, prefabricated sections put together nearby and then crane lifted into place would be the best option. This is our schedule here for the future. And any questions?
Is the
Yes, sir.
glulam decking,
What was that?
sorry, does the glulam decking actually require any protection, or can you just set it down?
Yeah, it's going to be treated as well. That'll be treated with the I think it's on that slide. Treatments. There it is. So decking and stringers, the pentachlorophenol, which is water repellent. So it'll help with the sustainability, which is really nice. But yeah, that's the most commonly used one, and yeah, it's much better than the alternate that I was telling you about.
Sorry.
All right, yeah, you eliminated your pier. Why did you do that?
Because we're using glulam stringers, and the benefit of the glulam stringers, they're much stronger and stiffer than other timber materials. They're designed for long spans, so once we do the testing, we can verify that that's going to work.
You increase the span, you increase the size of the member. I don't care if it's a glue laminated or a concrete or a steel. The size of your member gets larger when you increase the span. You have a pier already there. Why aren't you using it to reduce the span? Also, when you have a pier, it gives you a continuity in the beam, which is a redundant, which is required by code.
Okay.
So I don't know why you're eliminating the pier. What are you going to do with it?
Did you check up on the deflection? That's an addition to that.
On
Check on the deflection?
the report from the FHWA did state that the middle pier abutment was beginning to become structurally unstable. That was one of the reasons why it was structurally deficient. It was one of the reasons that were listed.
You cannot leave it in the middle of the river if it's structurally.
We would remove it. Have it removed beforehand when they're
10
removing
years
it.
with the EPA.
What was that?
You need 10 years with the EPA to remove anything.
Yeah. Yes.
Did you check on the deflection? Did you consider the deflection?
The deflection, that's going to be.
Once you remove that,
Well, that's what we're doing. The testing is done next semester. That's when we'll be putting it into STAT and finding out what the deflection is.
so what you have to be careful, see what Dr. Abud was saying is very important.
Yes, yes.
You can play around with the size, all
And the type.
the support. What I'm saying is this, the more the support, that means, of course, the size is going to be less. If you remove a lot of the support, it means you need a very large size. So these are some of the things you have to consider. That's why we have statically determined structure. You have lesser moment, because they are lesser moment because you have a lot of support. Therefore, the sizes will be smaller. But once you remove a lot of the redundant, you need a very large size. So don't be quick to remove any, you have to be careful about it.
So we're better off using that middle abutment, and it'll
You have
probably
to
drive
check up
costs
all that
down too.
before
We didn't
you
think
remove
about that.
anything.
All right,
I'm just supporting
Definitely.
what he's saying.
definitely utilize that.
I just want to ask you about this diaphragm. Go back to the diaphragm slide.
The vibrations?
No, diaphragm.
Oh, diaphragms, yes. This is from the USDA
Why are you
manual.
alternating the spacer?
I knew we should have put that in.
Stability. Why did you do that?
It's from the USDA manual. What they recommended they have a table and they have a diagram that I was going to put in, but we didn't add it. It was actually on the same page as this. It shows you that you want to, for the size, the overall bridge dimensions that we have, you want to have a line here that's 3 feet from the edge on both sides, and then 12-foot spacing in between. So that if it was a larger bridge, they would have had to do another section of diaphragms. But it said clearly that about that line, you need to alternate 6 inches on center between each glulam stringer.
And why is that?
I'm not sure, but this is what the manual told us.
So you said it's the USDA?
The
Department of
USDA.
Agriculture?
Yeah. What's the name of
Forest
it?
Service.
The Forest.
The Forest Service of that.
USDA Forest Service.
Okay.
Yeah.
They have design constraints.
They have a whole
manuals
manual
that would
for it.
apply to this bridge.
Yes, yes. That's what we used to base this off of, and then we figured once we can test it, we can determine whether this design will work or not.
Well, there's an NDS. Are you talking about the NDS? Because I know that that's the manual we use so much for wood. in the
Which
recent
manual
times.
would you say?
The NDS, which is produced by
NTS.
NDS.
NDS.
Yes, produced by the, I think, Department of Forestry.
Okay.
Because I know that's what we use now.
Oh,
I
shit.
teach wood also, so I know that that's the most modern documents we use.
We'll have to rent that then. Yeah, we've been using the AITC manual, the USDA manual, and the AASHTO.
I saw I did your mornings, okay.
Yeah,
But
definitely.
I know that
definitely use
NTS is what we use mostly now.
Wish we would have known that.